Good morning, everyone. Today we will start with fluid dynamics, in which we are going to study the fluids when they are in motion. So when a fluid is in motion, it's described by its flow, which can be characterized as being one of two types, basically, either steady or turbulent. So what do we mean by steady and turbulent? One of the best and famous examples, and the most easiest also, هو example السيجارة لما تكون بالمنفضة. كلنا مرق معنا أكيد بحياتنا العملية هذا الإكزامبل. نلاقي السيجارة لما تكون محطوطة بالمنفضة، أول شيء بتطلع على الدخنة بشكل كتير مستقيم على خط، and then نبلش نشوف إنه بلشت السموك تبع السيجارات وكأنها تتداخل مع بعضها كل الخطوط بشكل إنه بصير عنا هذا الإفكت. So in this picture we can already by eye distinguish between these two types of flow, a steady flow and a turbulent flow. So what do we mean by steady? We mean that each particle in the fluid, it follows a smooth path such that the paths of different particles never cross each other. So as you can see here, we can imagine this flow here as an ensemble of lines, and these lines, they are all parallel to each other, so that none of the particles of the fluid can go from one line to another. And then at some point, when the particles start to have some speed, their speed increase, and then above a certain value of the speed, the particles start to cross they start to cross from one line to another. So the lines which were in the steady flow parallel, they start to be mixed, and the flow in general becomes irregular, as we can see here in this picture. So when it becomes like that, we call it turbulent. So that's why we have to always differentiate between turbulent and steady. Now, what we are going to study in this chapter is the fluids in motion in general. However, fluids in general, they are quite complex system, and if you want to take real fluids, it's not that easy to describe them. So that's why in our studies in general in this chapter, we're going to make some assumptions, and these assumptions result in an ideal fluid flow. So what do we mean by an ideal fluid flow? We mean the following. We want to study the fluids in such a way that we understand everything, and the motion of the fluids is fully under control. So that's why we will consider first that the fluid is non-viscous. What does it mean, non-viscous? It means that the internal friction associated with the resistance that two adjacent layers of the fluid have to moving to each other is not present, or it's negligible. So فينا نتخيل نحن الفلويد عبارة عن layers، عبارة عن طبقات، وكل طبقة بتحف بالطبقة اللي على جنبها بالadjacent layers. فإذا كان هيدا الريزيستنس ما بين one layer والتاني كتير قوية، فبهالحالة هذه بنسميها الانترنال فريكشن. بهالحالة بنقول إنه الفلويد is viscous. أما إذا كانت هالinternal friction negligible, then we can say it's not quite significantly يعني pronounced, فبنقول إنه internal friction is neglected, and therefore the fluid is non-viscous. The second assumption we're going to make is that the fluid is incompressible. So when we say the fluid is incompressible, we mean by that the density of the fluid is constant. So whenever you take parts or samples of the fluid, you will find everywhere that the density is exactly the same. Then about the flow, we will make an assumption that the flow is steady, which means that the velocity of the fluid at each point remains constant in a steady flow. And all the lines, they are parallel to each other, and the particles moving on one line cannot cross to another line. And finally, the flow is irrotational. In few words, we can describe this, or we can explain this in the following way, that the fluid has no angular momentum about any point. But in practice, إذا كمان هذا الإكزامبل مارق معنا بحياتنا، اللي هي عموما بمية النهر أكثر شيء بتلاحظوا أوقات إذا كان في شيء بالنهر ماشي مثل الدولاب مثلا حدا عم يلعب، في محلات بصير الدولاب يبرم بخلال الموشن تبعه بقلب النهر. فلما يصير يبرم الدولاب او اي اوبجكت يعني about some point، فهذا الشيء بيعني انه the fluid is rotational. فلما نقول انه the fluid is assumed to be irrotational, we mean that there is no such experience or there is no such observations بالfluid. So when we say now ideal fluid flow, you know what do we mean? We mean that the fluid is non-viscous, so internal friction is neglected. The fluid is incompressible, so rho is constant everywhere, and the flow is steady and irrotational. Now, what do we mean by a steady flow? Here you can see a figure that shows more clearly what do we mean. So this, for example, is an ensemble of lines. So these lines, that we call them the flow lines or streamlines. And this streamline is defined as the path taken by a fluid particle under steady flow where the particle is moving. The set of streamlines or the set of flow lines, they form a tube, and we call it a flow tube or tube of flow, as you can see in the figure here to the right. Now, if we just zoom in a little bit on these lines, you'll see that the lines, they are parallel to each other, and any particle on a given point would be moving with the same velocity v. And one important thing is that the fluid particles, they cannot flow into or out of the sides of this tube, which means that particles, they cannot come into this tube or get out of the tube. This is something very important in the case of a steady flow, because that means as well that the particles, if they cannot flow in or out of the tube, that means that the mass of the liquid, the amount of the liquid is not is as unchanged as long as this fluid is moving. So, for example, if you consider a particle here, this particle cannot move neither out of the tube nor in. So let's consider it cannot go out of the tube and cannot go to another line. So it cannot cross one line to another. This is forbidden for a case of a steady flow. So let's now continue by discussing the motion of fluids. And here we will start with the first equation, which is, we call it the continuity equation. So in this continuity equation, let's consider a flow of an ideal fluid flow. So the fluid is moving from this side, it goes inside the pipe or this tube, and then it goes out and it continues. So what we want to study here is we are looking for an equation that relates the speed of the fluid in two different points, right, with two different cross-sectional areas. So if we have a pipe of non-uniform size, what do we mean by non-uniform size? We mean that at some point the cross-sectional area, the surface area of the tube, at some point it's quite small, we call it A1, and in other points it's bigger. It could be much bigger, it could be a little bigger than the first one, but they are different, and so the velocity will change as well. So the idea is that we want to see how much the speed increase or decrease if the cross-sectional area of the tube increases or decreases. That's it. So let's start. So consider that we are going to make some exercise, and this exercise we're going to study this sample. So looking at this sample, if we take one sample of the fluid that is moving, لناخد هيدي الشقفة من الفluid we will consider it, okay? And we will see how this part of the fluid is moving. So we'll see that at the point 1, this part of the fluid was moving with a given velocity v1, okay? And let's say that the fluid has displaced a displacement delta x1 at the point 1. And at this point 2, this sample of water becomes this blue sample. And this, we say that the fluid is displaced at the point 2 pi delta x2. So let's go on. Now the particles, of course, they move along streamlines, and we consider this to be a steady flow. So we consider an ideal fluid flowing through this pipe. Now in a given time interval delta t, if we just fix some time interval delta t, and then we want to see this sample at the point 1 and at point 2, what happens with, so at the point 1, we see that delta x1 is equal to v1 times delta t. So the displacement is nothing else than the speed multiplied by the time interval. Okay, and the volume of the water, so the volume of this sample of water here at the point 1, it's given by a1 times delta x1. So here we are dealing with this this sample. The sample is actually nothing else than a cylinder. So هو عبارة عن cylinder. الكروس sectional area تبعها السلندر هي A1 وطوله عمليا هو دلتا x1. فالفوليوم للسلندر هو عمليا الكروس sectional area multiplied by the height. هلا بهالحالة السلندر is horizontal, so the height is delta x1. So V1 is equal to A1 times delta x1. So it is equal to A1 times delta x1. We have just evaluated up there, so we replace it by its value, and so we end up with V1 equals A1 times V1 times delta T. So this is the volume of the displaced fluid at the input, or by input we mean the point 1. Okay. Now let's look at point 2 and what happens at the point 2. So in the same way, if we are going to look at the point A for a given time interval delta t, we will see that this sample of fluid has been displaced by delta x2 in a given time interval, and it's moving at the speed v2. So delta x2 is equal to v2 times delta t in a given time time range. The volume is also given the same way. So it's the height of this sample, which is given by delta x2, multiplied by the cross-sectional area of this sample, which is given by, which is here in blue, which is given by A2. So V2 is equal to A2 times delta x2. Delta x2 is equal to V2 times delta t. So we end up with A2 V2 times delta t. And this represents the volume which has been displaced at the point 2. Now the point is that since we are dealing with an ideal fluid flowing through this pipe, and in an ideal fluid, the particles in a fluid, they cannot come in or out, or get out of the fluid or get in to the fluid. يعني هدول البارتيكلز مثل ما شفناهم بالتيوب ما بيقدروا يغادروا او يفوتوا. لا بيقدروا يغادروا برات الفلو تيوب ولا بيقدروا ينتقلوا من نقطه على نقطه ثانيه. فبالتالي the amount of the the amount of the fluid did not change. الماس تبع الفلويد ما تغيرت من نقطة لنقطة. So we can simply say that M1 is equal to M2. So the mass of the fluid at the point 1, at the displaced fluid at the point 1, is equal to the mass of the displaced fluid at point 2. And this is what we mean by, so the mass that crosses M1 in a certain delta T, which is here, should be equal to the mass that crosses A2 at the same time interval. So we end up with the mass, don't forget that the mass is equal to rho times V. So don't forget that the density is nothing else than the mass per unit volume. So the mass is nothing else than rho times V, where V is the volume, of course. So rho of rho1 V1 is equal to rho2 V2. But since we are dealing with an ideal fluid flow, and the fluid is incompressible, therefore rho1 is equal to rho2 is equal to rho. So the density does not change in this fluid, and so we can simply get rid of rho1 and rho2 because they are the same rho, and we can make the equation V1 equals to V2 as A1 V1 times delta T equals to A2 V2 times delta T. Now again, delta T is the same because we are looking in the same time interval at the 2 points, so we end up with A1 V1 equals to A2 V2. So this is the so-called continuity equation for fluids, and this is valid at all points along a given pipe when we are dealing with an ideal fluid flow. We can write this equation in the following way as AV equals to a constant. But when we say AV equals to a constant, we mean by that we can apply it between any 2 points. And whenever you take point 1 and point 2 where to apply this equation AV equals to a constant means that if you evaluate it at point 1 will be equal to the same if you evaluate it at point 2. So the product of the cross-sectional area and the speed are equal. or the product is equal between any 2 points, not are equal. So that's number one. Number two, also this quantity A times V is actually called flow rate. So if you see a flow rate or discharge rate, etc., these variables mean the product between the cross-sectional area and the speed. And so if you have the flow rate and you have the cross-sectional area, for example, you can deduce the speed and vice versa. So this is it about the continuity equation. What we have seen here was just an example, and you can think of it as an exercise to understand how we get this continuity equation. However, when you want to use it in the problems, you are only required to know this equation, AV equals to a constant, or A1 V1 equals to A2 V2. I mean, both are the same, but you should apply here. This is what you should apply usually, but this is nothing else than the first one, AV equals to a constant, but applied between 2 points 1 and 2. Now we will move on with the Bernoulli's equation. So Bernoulli's equation, it relates the speed of the fluid in a given pipe. It relates to the pressure and to the elevation. So note that in the first exercise here, when we were looking for the continuity equation, we were only looking at the speed of the fluid at 2 different points where A is different. But still, this is not a very general case because, for example, the continuity equation doesn't tell us anything about the pressure at point 2 and point 1 and how they are related to each other. Also, this equation doesn't say anything about possibly the elevation of point 1 and point 2 with respect to a given reference. For example, I mean, if we consider this pipe is above the ground, like in here, for example, it's considered this is the ground, then you could immediately recognize that the point 1 is a given elevation y1 with respect to the ground, while point 2 is a different elevation with respect to the ground. So how this difference in the elevation would affect the pressure at point 1, point 2, and also the speed at point 1 and point 2. So this kind of information are not taken into account in the continuity equation, and that's why we need to discuss the Bernoulli equation. So our goal here in the Bernoulli's equation is to derive an equation between the speed of the fluid at 2 different points, 1 and 2, taking into account the pressure at this point 1 and 2, as well as the elevation. So let's start. Consider this system. Okay, so the fluid again is flowing from this side, from the left-hand side to the right-hand side, and it continues along. But what we will do here is we will cut. Actually, this we'll take only this sample of water, and we want to see what happens with this portion, for example. So we want to see, this is the point 1, and this is the point 2. We will want to see what is going on at the point 1 and 2, but the fluid is all the time moving. So let's consider the flow of a segment of an ideal fluid through a non-uniform pipe, which means that again, A1 and A2, they are different, in a given time interval delta t. So at this point 1, we have a given pressure, P1, and at point 2, we have a given pressure, P2. But we'll see later on what is the origin of this pressure at these 2 points, number 1. Number 2, also these 2 points, they are at different elevation with respect to the ground. So if we take this line here to be our y equals to 0 level, so you will see that the point 1 is at elevation y1 with respect to the reference level, while the point 2 is at different elevation, which is y2. So the idea now here is to be able to relate the pressure, the speed, and the elevation at point 1 together with the pressure, the speed, and the elevation at the point 2. We want to find an equation that relates all these variables together. So we will do it. Let's start. احنا قلنا هون بدنا نقطع هالفلو وبدنا نشوف شو عم بيصير على two faces of this sample of fluid. اللي عمليا عم بيصير هو كالتالي. اذا انتم تخيلتوا هذا الفلويد ماشي عمليا نحن هنوقف على هيدي الفيس للسامبل، هيطلع معنا انه هيدا البورشن او هيدا الفيس، يعني مع هي الفيس لهيدا التيوب عم تتعرض لضغط من الفلويد اللي جايه من ورا. فهالفلويد اللي جايه من ورا it exerts a force F1. F1 to refers to the point 1 اللي هو من اتجاه الشمال باتجاه اليمين، يعني من عم يجي من وراها هيدا الضغط. And this force F1 is perpendicular to the surface, as we know from the chapter 14 when we discussed the fluid statics, is that the force exerted by a fluid is perpendicular to the surface of contact with the object, which is in this case our here sample in the tube. And the magnitude of this force is nothing else than P1 times A1. So where did we get this? We get this from the definition of the pressure. So you remember the pressure was defined as the force divided by the cross-sectional area. So if here the fluid behind the tube exerts a force on this face of the tube, it means that F1 is equal to P1 times A1, where A1 is the cross-sectional area at the point 1. Now continue and let's have a look at what happens at this face in here, at the upper face of this tube. Since the water is flowing and it's just moving steadily, بالتالي هيدي اذا ما نحن عم نشوف شو عم بيصير على هيدي الفيس عمليا في المي اللي وراها، فالمي اللي وراها عم تضغط عليها لهيدي البارت. Also this F2 is perpendicular to this surface, to this cross-sectional area, and the magnitude of this force is given by the pressure multiplied by A according to the definition of the pressure. So we have here at both sides 1 and 2, F1 being the force exerted by the fluid on the left, and at point 2 F2 is the force exerted by the fluid to the right of the segment that we have selected in here in this tube. So in a given time interval delta t, this portion, or I mean this at this point 1, the fluid will move by delta x1 during a time interval delta t1 with the velocity v1, while at this point 2 it will be moving with a given velocity v2 in a given time interval delta t with a given displacement delta x2. Now what we want to do is to relate all these information. How? Actually, we will refer to the mechanics. This segment that we have seen is subject to the forces exerted by the fluid, both to the left and to the right side of the segment. So actually, we are going to use some parameters and some concepts that we did not yet went through in mechanics, but just take them as they are here in this course for the moment. So in a given time interval, we have seen that we have F1 acting by the fluid on the left on the segment, and F2 is the force acting by the fluid to the right of the segment. So these two forces, they produce some work, and this work is defined as the force multiplied by the displacement. So W1 is F1 times delta x1, and if you replace F1 by the value P1 times A1, so we end up with W1 equals P1 times A1 times delta x1. But here we are looking, if you just have a look at this portion, you would see that A1 times delta x1 is nothing else than the volume of this sample. So this is the cross-sectional area, and that is the height of this cylinder. And so A1 times delta x1 is nothing else than the volume. Okay, at the second side of the segment, we have W of the force exerted by the fluid to the right on the segment. So F2 is as well, W2 is as well equal to the force F2 multiplied by the displacement delta x2. But here we have a minus sign for the simple reason that actually in this case F2 is in opposite direction with respect to the displacement. So you see the displacement is on like that, and F2 is on the opposite side. So because these two vectors, they are in opposite side, we will have a minus sign. And this detail we will see later on when we talk about it in mechanics. So if you replace again F2 by its expression, we end up with P2 times A2. And again, A2 times delta X2, it's nothing else than the volume. So we end up with W1 equals P1 V1, and W2 is equal to P2 times V2 with a minus sign due to the fact that F2 and delta X2 are in opposite direction. So that is number one. Now, number two, or the second point, actually we'll see in mechanics that if we have a given object، بهالحالة الأوبجكت هو السيجمنت، هذا السيجمنت يلي شايفينه على الرسمة. Okay. If this object is a subject to different external forces, then the total work done on the system by the external forces is equal to the change in its mechanical energy. So in our case, this object هو segment of fluid. So we can deduce therefore that the total work done on the segment of fluid by the fluid which is outside this segment is nothing else than the change in the mechanical energy of this fluid. So in mechanical energy, we are dealing with two quantities basically. So the first one is the kinetic energy. So this K, it means, let me just specify. So this by K, we mean the kinetic energy. And by U here, we mean the potential energy. So U is nothing else than the potential energy. And of course, both kinetic and potential energy represents the mechanical energy. So let's have a look between point 1 and point 2. What is going on in terms of kinetic energy and in terms of potential energy? For the variation of the kinetic energy, it's given by delta K equals K2 minus K1. So it's equal to half mv2 squared minus half mv1 squared. For the potential energy, this is nothing else than mg. So you know the potential energy, it has the, so the potential energy has the expression m times g times y. So if we are determining the variation of the potential energy between 2 points 2 and 1, this will end up with mgy2 minus mgy1. So which means mgy2 minus y1. Okay, so this equation here will be the our starting point. But what about W? Don't forget that W is the total work. So it is the work done by the external force 1 plus the work done by the external force F2. So we'll have to add up these two terms. So let's do it. We will replace each term by its value in this equation. We end up with, طيب محل W حطينا W1 plus W2. So this is the total work done on the segment of fluid. This is the variation of kinetic energy of this segment, and this is the variation of the potential energy of this segment. W1 was equal to P1 V1, W2 was equal to minus P2 V2, is equal to, so for the kinetic energy, this was the factor half mv2 squared minus half mv1 squared, plus the delta U is given by mgy2 minus mgy1. So what we did here is the second, in the second line is the following, third line. So here actually don't forget that V1 is equal to V2. So why V1 is equal to V2? Because the volume of the fluid displaced at point 1 is equal to the volume of the fluid displaced at the point 2. عمليا إذا بهيدا قلب هيدا السيجمنت بناخذ portion of the fluid. هالبورشن عقد ما عم هون عم يحرك على البوينت 1 عقد ما عم يحرك عن بوينت 2 عمليا، يعني عقد ما عم بفوت على هالسيجمنت مي عقد ما عم يطلع منه مي. Let's consider that the fluid is just water. So V is the same on both sides, and so this yields P1 minus P2 and V in factor بنحطها تعطينا باقي الترمز. Now نحن بدنا نجيب البريشر بالنهاية، بدنا نشوف كيف هالبريشر عم تتغير مع السبيد وكيف عم تتغير مع الاليفيشن. So let's get rid of this V. خلينا نتخلص من ال V. كيف بنتخلص منها؟ بنقسم كل الايكويشن على V. So we end up with P1 minus P2 راحوا ال V equals to هون في عنا half. So هون اضطرينا نقسم كل الترمز by V. وال M over V هي بكل بساطة الدنسيتي. So we end up with P1 minus P2 is equal to half rho V2 squared minus half rho V1 squared plus rho Gy2 minus rho Gy1. Now the point is, if we just take all the factors which have 1 in, يعني كل الفactors اللي labeled by 1 خلينا نحطهم لحال، وكل شيء factors labeled by 2 خلينا نحطه لحال. Okay, so you will see that at the end P1 plus half rho V1 squared plus rho Gy1 is equal to P2 plus half rho V2 squared plus rho GY2. And here you just have a correction. I have a correction here. This is, of course, rho. It's not the mass. So this is the rho. Okay. So actually here we can already deduce, and we already arrived to our goal. We end up with P1 plus half rho V1 squared plus, so this is rho. So we end up with P1 plus half rho V1 squared plus rho GY1 is equal to P2 plus half rho V2 squared plus rho GY2. And this equation relates, as you can see, the pressure, the speed, and the elevation of two different points. So this could be simply written as P plus half rho V squared plus rho GY equals to a constant. And this is called or known as the Bernoulli's equation. And actually it shows the following. شو بتعني هيدا الايكويشن لما نقول هيدا equals to a constant؟ بتعني انه هدول الثري terms بيقدروا يتغيروا، بس بيتغيروا بشكل انه مجموعهم بضل ثابت ما بيتغير. يعني بمعنى اخر اذا كبرت البريشر حكما لازم يصغر يا اما الفي يا اما الواي يا اما اثنيناتهم لحتى يعادلوا زياده البريشر. او اذا البريشر نقصت لازم حكما السبيد والواي يتغيروا بشكل انه جمعهم يضل قيمته قد القيمه القديمه. So this equation shows that the pressure of a given fluid it decreases as the speed of the fluid increases or as the elevation increases, or both could increase as well while we have P decreasing. So this is it. One just comment about that is that this equation, whenever you want to apply it, you have to apply it between two different points. And when you want to apply it within two different points, so you will write down that this summation at the point number 1 is equal to the summation at point number 2. So in other words, you will write down P plus half rho V squared plus rho GY. So all of them, if they are evaluated at point 1, so they correspond to P1 plus half rho V1 squared plus rho GY1 is equal to P plus half rho V squared plus M plus rho G Y evaluated at the point 2. And so we end up with P2 plus half rho V2 squared plus rho GY2. So these two quantities should be equal, which means that if at point 2 the pressure has changed, then as well V2 or Y2 will be changing in the opposite direction, such that this sum remains the same, just like it was in point 1. One last comment is that we can have a particular case. So a particular case is when the velocity or the speed of the particles is equal to 0. So in this case, we consider a fluid at rest. So if we put V equals 0 in this equation, P1 plus half rho V1 squared plus rho GY1 equals P2 plus half rho V2 squared plus rho GY2, you will see that you end up with this equation, P1 minus P2 is equal to rho GY2 minus Y1. And this equation, this is nothing else than the fundamental relation of hydrostatics that we have seen at the very beginning of this chapter when we were studying the fluids at rest. Which is not quite surprising. I mean, this relation is nothing else than the variation of the pressure with the depth. If you have a particle at different elevation or at different depth with respect to another point, then their pressure varies in the following way according to this relation. So again, here what we have done in this section is that we have made a study of this tube, of this segment of fluid, and based on our study, taken into account the forces exerted on the system and the work done by these forces, also using the principle of conservation of the energy by writing W total equal W potential energy, delta potential energy and delta kinetic energy, the summation of these two terms, we ended up with this equation. However, you are only required to know this equation and you are not responsible of deriving it. يعني انتم بس مطلوب منكم كان انا هون حطيت لكم هالتفاصيل لان نقدر نفهم كيف اجت هالايكويشن ومن وين خلقت وشو بتعني كل ترم فيها وكيف قدرنا نربطهم ببعضهم. وانما انتم بالبروبلمز كل شيء انتم بس معنيين تعرفوا هيدا هو two terms. Equation, Bernoulli's equation, which says that or tells that the pressure and the speed and the elevation of two different points, they are related in the following way, such that the summation of P plus half rho V squared plus rho GY, this summation is always constant. And whenever you want to apply this equation, you will get this one over there. So this is what you should know from this section about the Bernoulli's equation. Now let's start with an application. Let's make an application about this Bernoulli's equation. So let's see here in this figure, which is figure 12.25. So this figure below, it shows a venturimeter used to measure the flow speed in a pipe. So we have a pipe here. We called actually this is called the venturimeter. You have a pipe of non-uniform cross-sectional areas, as you can see, so A1, and you have A2. You have to derive an expression for the flow speed V1, which is the speed of the fluid in this place where the cross-sectional area is A1, in terms of the cross-sectional areas A1, A2, and the difference in the height H of the liquid levels in the two vertical tubes. So actually, this big tube, is connected, or it's just open through two tubes. It's open to the atmosphere, basically. And we will see that according to the speed of the fluid inside this pipe, we will end up with different level of the fluid inside these tubes. So this represents the difference in the pressure, basically. Now the question is, we have to determine V1, which is the speed of the flow in the cross-sectional area A1. We have to derive this V1 as a function of A1 and A2, as well as the height H. And let's do it. So first of all, the flow is steady, as we know. So we assume that the fluid is incompressible, and therefore it has negligible internal friction. So the fluid is basically non-viscous and incompressible. We have to choose 2 points now where to apply Bernoulli's equation, because we know that the pressure in this the pressure at these 2 positions in particular, which is at this tube and this tube, they are different. And the proof, الدليل انه الليفل of the fluid بقلب هدول التو tubes هو مختلف، مما يدل على انه البريشر مختلف. وبنفس الوقت نحن هلا بدنا ننقي بحاجه ل 2 points basically. Let's call them point 1 and point 2. At these points we need to know and we need to relate the pressure with the speed at least. نحن بدنا نجيب البريشر مع السبيد، لانه البريشر هي اللي حتعطينا access على ال H، والسبيد هو الفاريبل اللي نحن بدنا نجيبها اللي هي ال V1 بهالحاله. So let's do it. Let's apply Bernoulli's equation. But what points we will take? Basically, we will take the following points. So هيدا أول point رح نسميها okay, I just call them A and B, but these A and B, they are nothing else than the 1 and the 2. So خلينا ناخد أول نقطة 1 تكون مباشرة تحت أول تيوب، بشكل إنه يكون في عنا access على البريشر. يعني هون على هالنقطة إذا بناخدها تحت التيوب، معروفة شو هي البريشر عليها. هي البريشر بأعلى نقطة زائد البريشر of the fluid column above this point. ونفس الشيء بالنسبة للنقطة 2 كمان البريشر معروفة عليها. فإذا طبقنا برنوليز equation ما بين البوينت 1 والبوينت 2، عندنا من ناحية access على السبيد V1 and V2، وعندنا access على البريشر P1 and P2. So this is what we need. That's why let's make it. So let's apply Bernoulli's equation to points 1 and 2. We end up with P1 plus half rho V1 squared plus rho GY1 is equal to P2 plus half rho V2 squared plus rho GY2. Now the problem, we can make some simplifications when we choose the points. So first of all, we chose the points 1 and 2 to be on the same level. إذا كانوا اثنين نقطتين على نفس الليفل، يعني على نفس المستوى، هذا الشيء بخولنا أنه نتخلص من الترم اللي فيه elevation y. Well, this is the case. ما أنه ال 1 with 2 they are at the same level, that means that y1 is equal to y2. And so since y1 is equal to y2, we can simply consider these 2 terms to be equal, and therefore we can get rid of them. Okay, then this reduces to P1 plus half rho V1 squared equals to P2 plus half rho V2 squared. Now we are looking for V1. Okay, V1 is our unknown. But here in this equation, we have both V1 and V2. So we have to find a way, just any way, so that we can write V2 as a function of V1. But don't forget that we can always use the continuity equation, and the continuity equation, it relates the cross-sectional area to the speed. So in other words, if we take this, the continuity equation to points A and 1 and 2, like this, so we can write down that the A1 multiplied by the speed V1 is equal to A2 multiplied by the speed V2. So the speed in the part of the tube where the cross-sectional area is A1 is different than the speed in this part of the tube when the cross-sectional area is A2. So from this equation, we can deduce that V2 is equal to A1 over A2 times V1. And so we can replace this V2 by its value inside this equation. So we end up with only one unknown, اللي هو V1 squared. يبقى عندنا that we need to determine P1 and P2. Okay, but for to determine the P1 and P2, all what we need to do is to use actually the fundamental relation of hydrostatic. And the fundamental relation of hydrostatic, what does we know? We know that the pressure at point 1 is equal to the pressure at the top point اللي هي أقرب نقطة بنعرف شو هي البريشر عليها، هي النقطة اللي على السيرفيس of the tube. نعرف إنه على السيرفيس of the tube the pressure is nothing else than the atmospheric pressure. So it's P naught plus rho of the fluid, which is here, I think it's the water, times G times H1. Let's call this H1, the level above the point 1. And at the point 2, we will have the pressure at point 2 is also, so again, we have to look at the point 2. What is the closest point where we know the pressure? It's at the surface of the fluid in this tube, where actually it's also the atmospheric pressure, because these two tubes are open to the atmosphere. ما انه open to the atmosphere يعني مثل ما هون هي كانت atmospheric pressure كمان هي هون atmospheric pressure. So it's P naught plus ما فوق ال A2 ال point 2 هي H2, فإذا plus rho G times H2. So now we know everything. We know P1, we know P2, we don't know what is V1, it's unknown, but we can write V2 as a function of V1, and that's what we are going to do. So we do it. Look what we will get. We end up with, so P1 plus half rho V1 squared is equal to P2 plus half rho A1 over A2 times V1 كلها squared. إذا بنجمع كل شيء محل حاله بيطلع معنا هون في عنا V1 squared واللي هي الأنون، وهون في عنا صار في V1 squared اللي هي الأنون. لازم نجمع هيدا الترم مع الترم اللي موجود هون. سو بنجيب هيدا الترم كله لتاني جهة من الإيكويشن بصير في عنا نيجاتيف ساين. وبعدين بنحط البريشر كمان لحاله بصير في عنا هون P1 minus P2 is equal to half rho V1 squared times A1 over A2 squared minus 1. So again, we have written already P1 and P2. So if you just make the difference between P1 and P2, you will end up with rho G times H1 minus H2. And if you look back at this figure in here, we called this point, so this height, we called it H1, and this height, we called it H2. So just by simply looking at this figure, you will realize immediately that H1 minus H2 is nothing else than H. الفرق ما بين column of water on top of point 1 and that on top of point 2 is nothing else than H, which is the difference in the level of the liquid and the levels of the liquid in the two tubes. So we end up with the following equation. P1 minus P2 is given by rho GH. بنحط rho GH بقيمتها بهيدي الإيكويشن. بيطلع معنا half rho, so it's equal to half rho V1 squared A1 over A2 squared minus 1. Again, rho, it's present in both sides of the equation, so we can get rid of rho. بيبقى عندنا فإذا V1 squared هي 2 times GH divided by this whole factor. And this is it. So we could express V1 as a function of A1, A2, and H. هلا إذا حدا حيفكر إنه بس نحن في بقلبها الجي يعني هيدي الإكسبريشن هو ما قلنا to express it as a function of G. G is a known variable. It's always a known variable. فبما أنها known معروفة ما بحق لنا يعني ما في مشكله انها تكون بقلب الايكويشن لانه هي معروفه شو هي، ما فيها اي مشكله. وانما اذا كان في عندكم فاريبل مثلا مثل اللي نحن دخلناها بايدنا مثل الاتش 1 والاتش 2 وبقيت مستمره معكم بهيدي اخر جواب، معناتها بكون في مشكله، لانه هول الفاريبلز نحن دخلناهم بايدنا لحتى نشتغل فيهم، وبالتالي مش مزبوط انه يطلعوا معكم بالفاينل ريزلت لانه we don't know what they are. So when they say as a function of variables 1, 2, and 3, you should stick to the variables 1, 2, and 3, except if you have a known variable like in the case of the gravity acceleration اللي هي g. So this is it. Whenever you have a given system and you want to determine the speed at two different points or a given point, given that you know the difference in the pressure or difference in the elevation of these 2 points, then you will need to use the Bernoulli equation as we did in here. And this venturimeter is quite known system and quite known application, this kind of systems. Okay. So this is it for the fluid dynamics. I just want to get back a little bit about the different topics. So you essentially need to know what is a streamline, the tube flow, etc. So you need to understand the introduction and what we are taking exactly in here. However, in the sections about the continuity equation and the Bernoulli equation, you are simply required to understand the analysis that we did here, or it's kind of an exercise. So we did 2 exercises. The first one, we have taken this sample or this segment of the fluid in order to show that the continuity equation is given by AV equals to a constant. And don't forget that this AV equals to a constant is simply called the flow rate, or it may be in some places could be called discharge rate as well. So in both, I mean, flow rate or discharge rate, both means AV equals to a constant. And so all what you need to know from the continuity equation section is that A1 V1 equals to A2 V2, this equation. Bernoulli equation section, again, here we have done another exercise where we showed and we made the proof of the Bernoulli equation so that at the end we could derive an equation which relates pressure, speed, and elevation of the fluid at 2 different points. And we have seen that actually through this equation is that if the pressure of the fluid changes or increases, for example, we should definitely have a decrease in the speed, in the elevation, or in both. So it depends on the value of this increase, such that the summation of the pressure half rho v squared rho gy should be always equal to a constant, should not change. The summation should not change, but any element inside this summation could change. So this is it for this chapter. Now we will move with the problems about the fluid dynamics.